Sorry guys. Hey guys, it's me Nathan guys. As you can see guys, this is my digital diaries 3 for tax 1 and 2. Now for tax 1, they gave me a picture. Now for tax 1, it shows an inferred spectrography graph where the x-axis represents the wave number cm-1 and the y-axis shows the percent transmitted. Each peak in the spectrum corresponds to a different molecular vibration, which can help identify functional groups within a compound. To analyze this spectrum further, identify key peaks, especially those with high intensity, as they indicate strong absorbance. Compare those peaks with known ion absorption ranges for common functional groups. And then you now have, okay, so examine the molecular formula. So the molecular formula provides information about the types and numbers of atoms present in the molecule. This can help determine degrees of unsaturation. So an O to an H stretch. So identify significant peaks in the IR spectrum that corresponds to functional groups. So there are typical IR regions for common functional groups. So you have an O to H stretch. So the broad peak around 3,200 to 3,600 centimeters -1 indicates the presence of hydroxyl, alcohol, or phenol groups or carbonylic acids. Then you have an N to H stretch, which is around 3,300 to 3,500 centimeters -1. The characteristics of amines and amides. Then you have the C double bond OH stretch, which is a sharp peak around 1650 to 1750 cm-1, indicates a carbonyl group commonly found in ketones, aldehydes, carboxylic acids, or esters. Then you have a C double bond C stretch, which is around 1600 centimeters -1, could indicate an alkaline or aromatic ring. They have a C to H stretch around 2800 or 3000 centimeters -1, typically indicates alkalines, while C to H stretches just above 3000 centimeters -1 suggest alkalines or aromatics. So match peaks to functional groups. So if I look at the major peaks in the IR spectrum to what they send me to assign functional group, a strong peak is around 1700 cm-1, might suggest a carbonyl group, and in the broad peak around 3,200 to 3,600 cm-1 could indicate an OH group. Then using the molecular formula, so now I should show my work. So the molecular formula is C4H8O2. That's for task 1. So calculate degrees. So the formula for this is 2C plus 2H minus 2, and then that 2 you plug in 4. So 2 times 4 plus 2 minus A over 2. They have A plus 2 minus A over 2. And that's 2 over 2, which gives you 1. So yeah, so a DUA of 1 means there's either one double bond or one ring in the molecule. And then the broad peak is around 3,200 to 3,600 cm-1. So this typically indicates an O to H stretch. Possibilities include an alcohol OH group or a carbonyl acid COOH, then a sharp peak here, and then the strong peak, which is around 1700 cm-1. The characteristics of a C double bond O carbonyl stretch, that's a sharp peak, and then given the presence of both O to H and a C double bond O, a carbonyl acid is a strong possibility, and ester could be considered but wouldn't typically show the broad O to H stretch. No peak around 3,300 centimeters -1 for N to H. Since we don't observe a peak here, it's unlikely there is an amine or an amide group in the structure. Then C to H stretch around 2,800 to 3,100 centimeters -1. Peaks in this region suggest the presence of alkanes or saturated hydrocarbons, and then propose possible structures. So option 1, a butanoic acid, which is C4H8O2. The structure for that is CH3, CH2, CH2, COOH. This molecule contains a carbonylic acid functioning group COOH, which will give a broad O to H peak around 3,200 to 3,600 centimeters, -1, and a C double bond O stretch around 1,700 cm, -1 degrees or of saturation. The carbolic acid group provides 1 degree of unsaturation, matching our calculated DOU. Then option 2, you have a methyl propionate, which is C4H8O2, structure CH3CH2COOCH3. This molecule contains an ester functional group R to COOR, which will give a C double bond O stretch around 1,700 cm, -1. Esters generally do not show a broad O to H peak, but some esters can sometimes show weak hydrogen bonding peaks if impurities or specific interactions are present. The ester linkage provides 1 degree of unsaturation, again matching the DOU. And then, based on the ion spectrum and the molecule formula for C4H8O2, which is for task 1, based on what I've seen, the two most likely structures are butanic acid and methyl propionate. And then, now this is for task 2. This is for task 2 now. So for task 2, the image I saw for task 2 is that it shows a proton nuclear magnetic resonance spectrum for a compound with the molecule formula C8H8O2. The table in the image provides chemical shift values in parts per million ppm and integration areas, which give insights into the environment of each hydrogen atom in the molecule. Okay, so the degrees of unsaturation, that's 5 subjects, multiple rings or double bonds. And then the peaks is at 7.78, 7.22, and 7.11 ppm. These shifts are in the aromatic region, approximately 6.5 to 8 ppm, indicating the presence of an aromatic ring. The integration areas 0.19, 0.10, and 0.19 suggest these peaks correspond to 4 hydrogens in total. A common structure with 4 aromatic hydrogens is a monosubstituted benzene ring, where these peaks could represent hydrogens in different electronic environments due to substitution. Peak at 3.58 ppm. This peak falls in the region typically associated with protons or carbons attached to electronegative atoms like oxygen. CH2 group attached to an oxygen atom. The integration area of a 0.30 indicates that this peak corresponds to 2 hydrogens, likely a CH2 group. Option 1. So, based on the IR data and the 1H NMR analysis, we can suggest the following structures. Option 1. A 4-hydroxybenzaldehyde, or it can be known as a power hydroxybenzohydrate. The structure that is a benzene ring with a hydroxyl group OH and an aldehyde group CHO in power positions. The benzene ring accounts for the aromatic peaks around 7 to 8 ppm. The aldehyde group could shift the aromatic position protons slightly upfield. A CHO aldehyde proton will typically appear around 9 to 10 ppm, but it may be absent here or shifted due to overlap. This structure fits with the formula CHH8O2 and a DOU of 5. Or option 2, you have a methyl 4-hydroxybenzoate. Okay, the structure of that is a benzene ring with a hydroxyl group OH and an ester group COOCH3 in power positions. The aromatic positions protons will appear as peaks in the 7 to 8 ppm range. The OCH3 group will appear around 3.5 ppm, which matches the peak at 3.58 ppm. This structure is also consistent with the formula C8H8O2 and a DOU of 5. Based on the NMR data and the molecule formula CHH8O2, what I've seen for tax 2, the image, the two most plausible structures are 4-hydroxybenzyl hydrate, and methyl 4-hydroxyl benzoate. And then you see then the DOU isulfur, so 2 times 8, 16 plus 2 minus 8 over 2. 16 plus 2, 18 minus 8, 10. Then 10 divided by 2 will give you 5. The aromatic regions are 7.78, 7.22, and 7.11 ppm. And the peak suggests a CH2 or its OCH3 group attached to an oxygen or electronegative atom at the peak of 3.58 ppm. And yeah, I already explained everything. So I'm going to put in for tax 3, but I gotta get a drink of water first. Need to drink water first. Yeah, I need to drink water first, guys. Okay. Now, this is for tax 3. So for tax 3, my favorite atom is a 1-octene. This is the structure. And then for B and C, I named 4. I just feel that 4 isomers will be equal. So the first one's an E2-octene, a Z2-octane, a E3-octane, and a Z3-octane. So that's for B and C. C is just to name them. Then for number D, okay, so for number D, I put the least stable one is Z2-octane. They have E2-octane, Z3-octane, and E3-octane is the most stable for number D. So I'm going to explain my reasoning for that, okay? So I'm going to most likely explain my reasonings for those ones. So a Z2-octane, the double bond is located between carbons 2 and 3, and the axial chains are on the same side cis, causing steric hindrance between the two bulky groups near the double bond. This configuration is relatively unstable due to steric strain. Then an E2-octane also has a double bond between carbons 2 and 3, but the substituents are on opposite sides trans, which reduces steric hindrance and makes it more stable than Z2-octane. And in the Z3-octane, the double bond is now between carbons 3 and 4. Since this bond is more internal, it adds stability. However, the cis configuration still introduces some steric hindrance, making it less stable than the trans form. And then the E3-octane, this compound has the double bond in an internal position between carbons 3 and 4. And the substituents are on opposite sides, minimizing steric hindrance. This is the most stable arrangement among these isomers. So I already listed them out for D. Then this is E. This is my work for E. So this is the reaction with HBr ether at room temperature. So this is for E. And then for F, okay, so the first one, the first percentage, that's at reaction 1. Reaction 1's the first percentage. So temperature is 0 degrees, they have 71%, okay, and a 29%, I guess. And then you have 40 degrees, 15, and an 85. That's what you have, okay? That's for F. Now, for F, I know, okay, so now I'm going to answer whether the reaction is regioselective or regiospecific. So the reaction of an alkane with HBr is regioselective rather than regiospecific because, however, regioselectivity refers to a presence for the formation of one constitutional isomer over another. In the case of HBr addition to an alkane, the reaction favors the formation of a product where H attaches to the carbon with more hydrogens, the less substituted carbon, and Br attaches to the more substituted carbon following Markov-Nivox rule. This preference makes the region radioselective, and a radiospecificity implies that only one possible product can be formed to the exclusion of all others. In most cases, hydrohalogenation reactions with HBr are not strictly radiospecific because minor products can sometimes form, especially if rearrangements are possible. Therefore, the HBr addition to an alkaline at room temperature in either its region selective favoring one product over others, but it's not region specific as minor products may still be possible under certain conditions. So this is for F. Now G, for G, which is the next page. This is my structure for G, however. I just drew a structure for G. This is the structure what it looks like for G. And then for H, predict which form of spectroscopy will you use to distinguish between the starting material and the product. How will this spectroscopic method allow you to complete this distinction? So to distinguish between the starting material, the alkaline, and the product, the alkyl halide, proton nuclear magnetic resonance spectroscopy and infrared spectroscopy will both be effective, each providing unique indicators of the reaction's products. So an HNMR spectroscopy is especially helpful in distinguishing between an alkaline and an alkali halide because of distinct chemical shifts associated with alkenic and alkyl protons. Starting material, which is the alkaline. Alkenic protons generally appear downfield in the theta 4.5-6.5 ppm range. This peak is characteristic of the alkaline group and it will be absent in the product. And then you have the product, which is the alkyl halide. In the product, the alkyl proteins bonded to the carbons near the halogen will shift slightly downfield compared to the regular alkyl protons. The absence of peaks in the 4.5 to 6.5 ppm region indicates that the double bond is no longer present, signaling the formation of the alkyl halide. Then you have an IR spectroscopy. Then an IR spectroscopy, the starting material alkaline shows a C double bond C stretch around 1600 to 1680 cm -1. Alkalines also have a double bond C to H bending vibrations that appear in the 900 to 990 cm -1 region, often associated with E and Z configurations. In the product, C to C stretch and C to H bending peaks will be absent, indicating the loss of the double bond. A new CBR stretch may appear around 500 to 700 cm -1, though it's often weaker and may not always be easily observed in the iris. So the HNMR spectroscopy will be the most effective method as it allows clear differentiation based on the disappearance of alkenic protons and the shift of protons near the bromine in the product. Our spectroscopy could serve as a complementary technique confirming the absence of the alkaline C double bond C stretch and possibly identifying the presence of CBR in the product. So this is all, guys, for my digital diaries. I hope you guys find this helpful and I hope you guys have a great rest of your day, guys. Bye bye.